this part here.
Sports gear, dyneema. It's the ultra.
So what I did was I moved it a little over so you could see me say dyneema. And then the timing is ultra high, like I'm saying this word here, right? And so it wasn't really timed like perfect, which I don't care that much. But I think you'll see.
Dyneema. It's the ultra high molecular weight polyethylene, or humpy for short.
So humpy is this word right here. And just because another concern I had was it was like you zoomed in, which is great, but it's too much of one thing at the beginning. It needs to jump around a lot. So
let's get about one type of rope material that is being used in more and more of our sports gear, dyneema. It's the ultra high molecular weight polyethylene, or humpy for short, known as the world's strongest and lightest fibers. It is 15 times stronger than steel, yet floats on water. Dyneema is the brand name by. So
that's the polished version, and you can see here how I did that and how I typed that. Now, something about the words. Use 15 stroke. I think you add 8 on a lot of them. It's just what I've been using, and it's super easy to see. It might be a little bold, but whatever. All right. The rest of this, all this was good. All this was good. I actually,
rope by
I would love
and reduce the strength.
Video from you on how you do that with the images. I don't know if that's an After Effects thing or if that's something I can do in Premiere. I like that.
Well, if you can't.
So the next thing is at 227.
To not come out. Otherwise, it just slips right out. Now, a fid, or which are supposed to not come out.
This isn't coming out. This is, that I think is the Brummel. This is an old video, right? This is talking about when the Brummel thing. Let me see here.
Holding all the pressure. However, being super slippery, it has to be buried long enough in order to not come out. Otherwise, it just slips right out. Now, a fid, or...
Yeah, that test was to show that a Brummel wasn't great. So I'm gonna eliminate that. And what we would show, right there. That's the money shot right there.
Here, right? Camera here.
All right. So that's the money shot, right? 1837 is on that video.
Out. Otherwise, it just slips right out. Otherwise, come out.
Boom.
Otherwise, it just slips right out.
And what I would do...
Now, a fid...
I'll just eliminate the word now.
A fid, or what you're supposed to bury this with, is supposed to be 21 diameter.
I know where you got these files. I will take care of that later. I'll download what I told you to download and do that. Okay, I would, so 250.
Oh, I'm gonna need to do about 200 and something millimeters in order for that finger trap.
So I'm gonna add the exact math, right? Like 240 millimeters equals XYZ. I'm gonna add that on top of me saying that. So you don't have to worry about that. Let's go to 3 minutes and 21 seconds.
Distance, cut that, do it again down here, cut that, and get it to gradually get down to almost nothing.
So, B-roll timing. Something seems off here. Let's see here.
A single strand at a certain distance, cut that strand at a certain distance.
So I'm looking at it, right? And it's okay because I finished my thought, but at that point we need to show the thingy. So let's see.
Cut that, do it again down here, cut that, and get it to gradually get down to almost nothing.
So let's see here, let's see.
At a certain distance, cut that, do it again down here, cut that, and get it to gradually.
And they'll just
get down to almost nothing. So as it goes.
So that's how I would use that, right? It just is based on the words and the timing. And that's just how I chose to do that. Okay. So 4 to 48, I'm just letting you know when you see something like this is me talking about
gear. Actually spliced all these from the dyneema that he sells. So he cut up a bunch, he made all these samples for us, and it took him hours and hours and hours.
So this is Extreme Gear. This is the Extreme Gear commercial. I would B-roll John and his adventures in Iran and all that, so you don't have to worry about that when I do commercials. Move text down on 456. Okay, so let me show you what I want on this text.
D12 Max 99.
Oh, here.
Dyneema on there, including the D12 Max 99 stuff. Pretty good. We're using.
I would say this. Let's do Marlowe SK99 Max. I would say let's see what a screenshot like this looks like. Something that really brands it, because it has the words on there.
Dyneema on there, including the D12 Max 99 stuff. Pretty good stuff. We're using.
So that makes more sense, right? You're seeing the brand name, you're seeing whatever. Let's do this, and let's make the words look a little different. Learn how I do the words here. Again, let's do 15. And we're gonna break this down into easy to see, right? Because people are not fully paying attention. And let's make it a little bigger, and I like it more at the bottom. Maybe not where the timeline would be, but right above it. So easy to read. It's in whatever metric system they like. Let's see.
Stuff. Pretty good stuff. We're using 6mm diameter, and Marlowe says that it's.
Oh, by the way, I really like this clip right here.
Pretty good stuff. We're using 6mm diameter, and Marlowe says that it's 5,440 kilograms of average breaking strength for 53 kilonewtons. And a splice is supposedly going to retain all that strength. In our next dyneema video that comes out, we are also.
Now, this B-roll has me talking. Now, if this was just a second of me talking, that's fine, but this thing is 5 seconds of my lips moving, and it like doesn't, I don't say anything, right? It's not the words you're hearing. So let me come up with a different version. So this, I just am on the main, the main big video that has all the version 1 on it. And
that's true. In our next dyneema video that comes out, we are also testing all the qualities.
So what I'm doing is just like, so now I want a red rope because that's visually easy to understand.
Or we
So let's go, boom. So that moves around a lot, so I'm okay with that. Let's just do this.
In our next dyneema video that comes out, we are also testing all the qualities compared to each other. And it's SK60, SK75, SK78, all those SKs or qualities, we can kind of put up against each other and even tested this.
So just sort of like bam, 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 because this is the slow-mos of that version. If you didn't have this, obviously you don't need to do that, but that's just better than my lips moving. So just put 4 slow-mos from this part of the video where we're just pulling these things straight in line. It could be a red one, a silver one, a blue one, just so it looks like they're different ones and not just the same tests over and over. Let's see, that is, we're at 5 minutes, 5:30. So this is important.
John Fioroni from extremegear.org spliced all these together.
So these are judgment calls you'll have to make, right? Because you'll have to cut stuff, right? But obviously I filmed this at the lab, not knowing I would do a narrative. And so a lot of this is double speaking, right? So listen.
And I've partnered up with him to make the best sword we can possible, and we want to have a lot of in-house testing by the people who are not making this gear.
We've already talked about John. We've already talked about the fact he made it.
It's kind of nice to embed all this information into that website. He was curious if the Samson, the Marlowe, or the Tuflenberger suggestions on how to taper made a difference. But we also have a diagonal cut and no tapering here in order to find out how much a taper makes a difference. I'm also curious if a locked Brummel, which is one of our samples here.
So I didn't really bring up Brummels, but all of that right there, boom, gone. So now let's see if we need how much of this we want.
how much a taper makes a difference. I'm also curious if a locked Bravo, which is one of our samples here, makes a difference, because
Hold on.
cut end. How much a taper makes a difference. I'm also curious if a locked Bravo.
Obviously, that isn't the beginning there.
I'm also curious if a locked Bravo, which is one of our samples here, makes a difference, because I think that extra bend might make it break lower, but it doesn't come undone.
That clip I said is that old lab. I don't know where it is in here. Oh, is it this one? Ah. This is where I get sneaky. We'll just leave that for now. Okay.
Because I think that extra bend might make it break lower, but it doesn't come undone when it has cyclic loading. And none of these samples have any sewn thread in them, and that's not really needed to keep the strength. That's in order to keep.
You know what? The Bravo
Loading.
thing is such a rabbit trail.
Now none of these samples have any.
Let's do that.
Now none of these samples have any sewn thread in them, and that's not really needed to keep the strength. That's in order to keep the splice where you want it when you're not using it. So you understand the context of what we're doing?
So I think that was a great disclaimer, right? So that wasn't brought up anywhere else. It's not a new topic. That's a disclaimer. So, yeah.
When you're not using it. So you understand the context of what we're doing. We're pull slow testing it in our slack snap slow puller machine with a hydraulic, and we connect this directly, and we're connecting this directly to sock shackles.
Hear that?
And we connect this directly with a hydraulic,
So if I cut here,
and we connect this directly.
see, this is kind of what gives it away for me. When they get a dead spot in here, I'm figuring that's usually the thing. So
And we're connecting this directly to
I just said the same thing twice.
machine with a hydraulic, and we're connecting this directly to sock shackles because some of the eyes aren't very big.
So that's correct. Well, I timestamped this stuff and now I cut out a whole bunch. 30 seconds later is let's see here.
And sometimes the dyneema is so strong that it will bend a quick link or a bow shackle before it breaks. Here we have the no taper first, and you can see how much it goes from skinny to bulgy quickly, putting a lot more strain right here on the dyneema. What we're going to do is pull test it to about 4 kilonewtons and then let it settle for about 30 seconds to a minute. And this one's kind of set for a little bit. But what happens is it settles.
Okay, so this is
Is
this is me talking about, preloading it, right? Preloading. It's a lot of the same thoughts.
After we keep it at 4 kilonewtons for about 30 to 60 seconds, we will finally pull it and see what they break at. And we're going to make sure we keep it consistent.
Okay.
After we keep it at 4 kilonewtons for about 30 to 60 seconds, we will finally pull it and see what they break at.
That is,
And we're going to make sure we keep it consistent with everything.
obviously I'm trying to keep it consistent, right? And then this,
7 kilonewtons settling right now. After we keep it at
if
30 seconds,
we wanted to use this, I would say let's unlink that.
after we keep it at 4 kilonewtons for about 30 to 60 seconds, we will finally pull it and see what they break at.
But all this is just me talking too much.
To bulgy quickly, putting a lot more strain right here on the dyneema. What we're going to do.
So all of that talking is like all in here now.
And
So let's talk about this real quick. So I'd like to have 2 decimal places, right? So that was the first one, 23. There we go. And I'll just put the KN right next to that. So that's how we'll do that. Effects, text, stroke. And I'll show you what I'm going to do with this. Is I'm going to push no taper. And this way people can follow along. let's make it capitalized so it looks nice. Okay, so we're gonna stick that in the upper right-hand corner because it's mostly out of the way when I'm showing stuff. You can even make it a little smaller. And once we do this, we're basically going to copy and paste it all the way across the thing. Now, what I like to do is
finally pull it and see what they break at.
So for the whole test, right, and the whole review, so it'd be this, and then, so you know what test you're on.
Side of this loop. So apparently, the MBI.
So by the way, that was a lot of quiet time.
On the inside of this loop.
That's a lot of quiet time. Okay, so all the way to there. And what I would do is number 1. And if we're gonna be in that corner, let's do this. There we go. All right. So as people are scanning through, they can just scan and see what's going on. We'll even make it a little smaller so it's not so obnoxious since it's gonna be the entire time. Oh, that's laggy. There we go. Okay. I'll show you how to make this fast in just a second.
What they break at. And it always breaks 10 or 11 of the strands out of 12. And it broke where the taper ended here. Interesting. Now my hydraulic, quite couldn't do it until I really forced it. Wow. Is there really a...
I would say the hydraulic's not the focus of the video. Sometimes it is. You got to make that judgment call.
Almost 4 kilonewtons on that currently. That's neato. So stiff. So stiff.
So I only need 1 stiff, right? So let's take this over here. Otherwise, people think the whole video is going to be this long, right?
So stiff. Ugh.
Like, that's the thought I want you to leave with.
Crazy. That looks like polished plastic on the inside of this loop. So apparently, the MBI...
Yeah, still, I don't need, we grabbed 1 or 2 thoughts. So...
And it always breaks 10 or 11 of the strands out of 12. And it broke where the taper ended here. So stiff. So apparently...
And what's cool is I don't have to show the load cell now, right? In most cases. So, let's keep that number. This is great. It's great, great.
I vary this taper a lot more, so it goes through my pulley and directly into here. Otherwise, I lose throw, or the distance that I can pull with my hydraulic. This thing only goes up 49 kilonewtons, or about 11,000 pounds. This is to keep that thing from recoiling, and now I have to keep this chunk of metal from recoiling when our next sample breaks. So there's a lot that goes into how not to destroy things that you're not trying to destroy, and this keeps that stuff from flying. So I didn't want to eliminate one of the load cells, because I like having redundant load cells when the samples took so much work to prepare. So now we'll pull the second sample and see what happens.
I think that was all great. Everything I said meant something, right? So, delete. And by doing that, it makes our job so much easier. And then with this paper, 41.93, 41.93, and that's it. And we just got to figure out where to end it.
That was 41.93, substantially less than what we got last time. I'm so glad. 41.93, substantially less than what we got last time. I'm so glad I spent all that time setting up the 2-to-1.
I think that's funny, but we already said, you know, like they can see the thing. We got the number in here. So
I'm setting up the 2-to-1. It feels warm. Interesting that it did not break 2 of them. Usually it's just 1. This one is broken. 1.
That's the end of a thought. Now I'm just rambling.
So the same thing as before. These eyes will just fine. So it's not as good of a dyneema.
Yep, all those are just random thoughts. And boom.
Third, no taper test.
So this is a big thing, right? This right here.
Third, no taper test.
We don't need, that's me verbally saying it for anybody organizing version 1. You're going to see it in the corner, eliminating the need for this. You're going to see the number in the corner, eliminating the need for the load cell most of the time. So this is how we keep the videos tight. is magically this guy. Boom. Taper number 3 and 43.48. So you can see that it's pretty quick to actually do the numbers.
It's just one. Now that is an interesting result. That's the splice. I guess our bend radius isn't good enough. It's interesting. Is this?
So the splice is when you bury it.
Splice.
That's the eye.
I guess our bend.
They can see what it is too, right? Even if I said it correctly, that is, let's just do this.
In result, I guess.
Well, there we go. Oh man. Laggy computer.
Our bend radius isn't good enough. It's interesting, as this is not even stiff. Like, none of it's stiff. It feels very soft. I think learning that our bend radius is too small is actually worse than no taper is actually quite interesting, because I connect this to all sorts of things.
I think that's a great thought. I think that thought's over.
Let's see if we can improve on this. 43.48. Interesting. Started at 3, it went up, and then...
So I didn't say anything intelligent enough there. And then, boom.
So these first 3 results is the part I was most interested in. No taper, reduced it down 13 to 20% lower than the average breaking strength at 46, 42, and 43 kilonewtons. We got that range.
That's a good effort right here. Let me show you what we're gonna do. I'm going to give you these screenshots. Nope, wrong one. Nope, that's the entire thing. That is the no taper screenshot, making your life a little easier.
So these first 3 results is the part I was most interested in. No taper, reduced it down 13 to 20% lower than the average breaking strength at 46, 42, and 43 kilonewtons. We got that range. What's interesting is the eye and how you connect it and the bend radius the eye sees is as important as the taper, but we're supposed to be getting full strength out of this stuff, and we're not, so we're going to see if it gets better the more we're tapering it. It's about 5 days ago from filming this.
Okay, so that's the Extreme Gear commercial, right? So this data is only relevant for this period of time. So let's make it big enough to see. Come on, computer. Oh, it hates me. Oh my God. There we go. Let's try that. Let's see if it blocks my thing.
So these first 3 results is the part I was most interested in. No taper.
So as you punched in, I would say you could almost do that.
The part I was most interested in. No taper, reduced it down 13 to 20% lower than the average breaking strength at 46, 42, and 43 kilonewtons. We got that range. What's interesting is the eye and how you connect it and the bend radius the eye sees is as important as the taper, but we're supposed to be getting full strength out of this stuff, and we're not, so we're going to see if it gets better the more we're tapering it.
Now, it's kind of awkward to have me here in this blank space. So as you can see in my other example video that I did, that I filmed or edited last night, you want your head at the top of the screen there, right?
Is the eye and how we're not, so we're going to see if...
So let's just do like a medium version. It's like a punch out of sorts.
So these first 3 results is the part I was most interested in. No taper, reduced it down 13 to 20% lower than the average breaking strength at 46, 42, and 43 kilonewtons. We got that range. What's interesting is the eye and how you connect it and the bend radius the eye sees is as important as the taper, but we're supposed to be getting full strength out of this stuff, and we're not, so...
That almost needs to be punched in, if you know what I mean. Trying to eliminate how many of those I have. Boom.
Kilonewtons. We got that range. What's interesting is the eye and how you connect it and the bend radius the eye sees is as important as the taper, but we're supposed to be getting full strength out of this stuff, and we're not, so we're going to see if it's better the more tapering it. It's about 5 days ago.
Anyways, so that's like the first 3 tests. Okay, we're almost done. Here's a couple more thoughts.
With diagonals.
So
With diagonals.
that's where we would start it, right? Obviously, you know what to do with the text now, but man, even that's really long. Let's see if we can trim that down. There's nothing worse than a break test that takes forever.
Strand apart. For 3 tests, 1 strand apart.
So that, like, the thought's done, right? So we need to trim it off.
Ah, you can see this. You can see the strain right here.
Okay, so that's that's that.
Is all the way through, and that's what makes it spiral. And strands, we have two strands. There are two strands of 10 and 12 strands. Now, and because those stay in the system, this recoils, it looks like DNA. Oh, graph, a little interesting angle in there. And then zero, started at, almost 1. So 43 to 50 kilometers, it's quite a range. And you can see that eyes moving on 10, but even on the last test where it didn't move anything, that friction would cut it. In the system, and this recoils, it looks like DNA. Normal graph, had a little interesting thing going on there. And then it went to zero, started at, almost 5.
So there's nothing interesting enough. This is a judgment call that we're gonna cut off this video right there. I'm not gonna get into that too much. Let's get into the next thing. This was great. This was great. Again, you're gonna just take this. You're gonna drop that on there. Oh my gosh. And you're gonna make that bigger and you have all the information there. So I'm not gonna resize it right now. This is something I don't want in the videos. Nothing to do with the measuring stick because that's just so much extra information, right? It's already too nerdy.
This is a proper taper based on Marlowe specs.
Based on Marlowe specs, I said a thought.
So this is at 4 kilonewtons right now, almost 1,000 pounds of force.
Yep, we don't need to know that anymore.
We're gonna measure to see at how much more things are gonna have to stretch, or settle, I would call it, before it breaks. This does not stretch.
Yeah. Nothing to do with the measuring stick. So you're gonna have to go through and just cut out anything to do with that yardstick.
3, 4.
So right here.
This is a nice helix. Looking good here.
Looking good here.
Interesting. So
We don't need this because we're gonna have the number on the screen.
First results. So blocked wormhole number 3, 4.
I guess all that can go.
You can feel the temperature there. That's interesting. It's practically burning my hand right. That's too hot to hold. Really.
All right, so at the end, we're just gonna summarize the ending real quick. Obviously, we have to show the test, so the yardstick is okay here. We're just not talking about it.
Oh no! All right.
Come on.
All right. That is so warm. It's
We don't need to use the word all right. Those extra words make it just take forever. This number, obviously, you would just have up here. And you would call it diagonal cut 1, diagonal cut 2, whatever the thing is, or Teufelberger, right? If you were doing this one, you would write Teufelturper taper 1, Teufelberger taper 2. Anyways.
so warm, it's practically burning my hand right now. It's very, very shiny right here. And then this. Okay, that's here. And then this. Okay, that's too hot to any right here.
Right, I said nothing, nothing, and I said a complete thought right here. So.
That's too hot to hold. I can barely touch it.
Barely touch it. Okay, let's see what's next.
I mean, it's technically quite a bit more, but it's not 50. I mean,
We're gonna get nitpicky here.
technically quite a bit more. Technically quite a bit more, but it's not 50 plus. I mean, that graph is sick.
So let's get rid of that dead space.
Graph is.
Oh, I guess it's just to right there. Jump it a little harder.
50 plus. I mean, that graph is sick. Number 3.
And this, the numbers showing up on top of the last test. So like that's a real problem, right? That looks sloppy. So let's.
Number 3, label, start.
Right, so that's the break. You go about right there. Ah, this is very important. This is a very important thing to pay attention to. You gotta have the right test. This is definitely not the right test. You can literally hear it's slipping, right? All right, that's slipping. You can hear the audio. But this test is snapping. So something's wrong, right?
27 point.
And I have a feeling it's the guy that did my version 1 screwed up. But this is where you have to keep an eye out for that. Okay, so here's a major flaw in my system is whoever's doing version 1, it's very important they do it right. So you can see here
that graph is sick.
You can see like you're not hearing what you're seeing, right? The person who did this completely put in the wrong clip, right? And you can tell because it's obviously not slipping. The theme of the previous test was that it was slipping out, right? So everything, it's a problem. It's a problem when people don't do their job right the first time because then it affects us. But this is how version 2s go. So in the iPhone 13, which is all my main stuff, this is my B-roll. This is my slow-mo. It's not that hard to find footage. And I believe all of this was in the folder. But anyways, you can tell like these are the other tests and this was in the middle. But yeah, that was supposed to all be in order. So the 12, the 9, and the 13 cameras are ready to, you know, in order. Anyway, so right before it starts slipping, let's do that. So that's the whole break, right? So let's just get rid of the number because that number has to be changed anyways.
27.40.
So let's just get rid of that. And let's this is the whole file. So let's just take the whole thing in there and cut it up.
Sick.
And if we want to be cute and clever, because we don't do anything for a little bit there, let's control copy, control paste, and then I don't do this very often, but here is a trick that I like to do. And then I'll cut it off here, which means I have to copy it again in order for it to link up right, speed duration. And then what I can do is if I really am trying to get fancy here, desktop plug, let's have not two arrows. This is an arrow I use. I don't really care what arrow is used. So what I could do to back this up is probably punch in a little. Because this is not the slow-mo, I can punch in, right? Which means I screwed it up, which means I could do that. This makes this take longer. So I'll go forward now. I'll take that. So this is what it looks like. So now
27.68. 27.48. 27.48. 27 point.
Cut that.
27.48.
I'm going to show that just because the graph is so interesting and it's not just a boring graph. And then let's review
There's some.
Do I say anything
This
interesting?
side is still bomber. Very, 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 very stiff. Here we go. Very, very stiff. And this side is still bomber. Very, 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 very stiff. Here we go. Very, very stiff.
Like, that's the ending thought before we get to... I guess with that, I would eliminate anything else. Yeah.
As you go to our next video.
So right when I stop going forward is the end of that video. And then I'll do video effects, not effects, video transition to solve. Dip to black. No. So then as we go, we do this. I'd almost make it tighter so it looks like my hand covered the screen. There we go. And that's it.